Projects 2, Group 1. The name of our project is Hindsight Blind Spot Monitoring System. So the purpose of our project was to design an attachable blind spot monitoring system that aims to increase the awareness of skiers and snowboarders with impaired hearing. And we achieve this by using an array of sensors that monitor the blind spot of the user, and when another skier or snowboarder enters their blind spot and is detected by the sensor, they get a non-visual vibrational signal. So here up on the screen we have two diagrams that show core concepts of the operation of our device. First on the left we have a top-down view. The black circle in the center is the helmet or the user. They're facing up, and Hindsight is the gray shape mounted to the back of the helmet. Here the blue circles represent other skiers or snowboarders. We designed this device to have distance-based vibrational feedback. And what that means is that the circle on the left, which is closer to the user, will cause a more intense vibration as opposed to the circle on the right, which is further away, which causes a less intense vibration. On the right we have a diagram with the same view, and what we designed this device to have is a 5-sensor, 3-vibrational zone arrangement. And what that means is that the two sensors on the left will cause the motors on the left side of the helmet to vibrate, the center sensor will cause the center motor to vibrate, and the two sensors on the right will cause the right zone of the helmet to vibrate. Here on the left we have our CAD model, one with a 2-piece tether design. The top part has our 5 sensors and our means of attaching to the helmet. It's connected through wiring to our component housing shown here on the bottom. And on the right we have our final design we used during one of our testing sessions.
So skiing and snowboarding is a very popular activity. In the 2018-2019 skiing and snowboarding season, there's about 10 million participants, averaging about 5 visits per season. So an activity this popular, a big thing is injuries. And many of the main injuries are collisions with other riders. And one way that we thought to prevent this was utilizing Hindsight blind spot monitoring system to create more spatial awareness for the user and create a safe and enjoyable experience for everyone on the slopes.
So when we set out to do this project, we needed to outline some mechanical requirements. The first requirement was to have 3D printed housings. These would serve to protect the internal electronic components from the external environment. We also didn't want to compromise the integrity of the structure of the helmet, and we wanted to use a battery that was rechargeable that would last approximately 8 hours. Most importantly, we didn't want to make the user uncomfortable due to added weight on the back of the head due to the device. If we move over to the electrical/software side of the requirements, we want to be able to detect objects up to 8 meters away from the user. And we want to orient our sensors such that we can get a 90-degree field range of measurement behind the user. We're going to be alerting the user with a clear non-visual cue. In this situation, that's going to be vibration. The vibration will allow the user to tell approximate location and distance of the other rider behind them. This is going to operate on a small microcontroller and have an on and off switch.
So a good prototype relies on the components that it's made of. And here we listed the components that we use to create our device, which include a 6-volt battery, a voltage regulator. We have here also 5 TFLUMA LiDAR sensors, a power switch, we have vibrational motors, and our TNC 4.0 development board. Here we have displayed a simple diagram that shows how our logic flows. Basically, once the device is powered on, we see the device begins to scan objects. If someone is detected in the blind spot of the user, will be warned with a soft vibration that someone is in the blind spot.
So this is our work breakdown structure. We have it broken out into 4 groups, which is our mechanical, electrical, testing, and management. And here's our fall 2022 schedule. This was key in keeping us being able to submit our deliverables, including prototype, testing, final report, and final presentation.
So that's for our budget overview. Out of the $500 total that this project was allotted, we used all but $105.46. If you look on the pie chart on the right side of the screen, most of our money went to purchasing our sensors. As to the cost of the university, our project over the past 2 semesters cost $394.55. If you want to source these materials yourself and build your own Hindsight system, it would cost you $305.83. This is lower than the cost of the university due to the fact that some of the purchases were strictly for research and development.
So diving into the mechanical design of this assembly of our product, here in this picture we'd like to display that we have 3 main components. We have our vibrational sensors, we have the sensor housing component, and also the component housing, which is connected with the tether. Diving directly into the sensor housing, it's important to notice that this was 3D printed and our sensors are held in place using M2 bolts. Also, the device is
vibration motor has a corresponding sensor that's mounted on the back of the helmet. So we have our right, left, and center zones. In the picture on the right, you see that the vibration motors are taped to the inside hard foam of the helmet. That's what we decided to put them. And then we have the soft padding that goes over them for more comfortability for the rider. Next is our component housing. So this was a 3D printed box to neatly compact our different electrical components, including our TC board, the battery, and our rat's nest of wires there. So this is key to being able to keep the electrical components safe by putting them inside a backpack or putting them in a special hoodie pocket. And then next is our attachment to the helmet. Our first step on the top left is by using heavy-duty Velcro, similar to what you would use for your Easy Pass on your windshield. Next, as Mark talked about, there's the groove or slit in the back of the sensor housing to put the goggle strap. And once you put those two things together, you see in 3 and 4, putting on the goggles actually creates an even tighter and more secure hold to the helmet for the sensor housing.
So to get to our final design, we went through 3 iterations of our prototype. The first one shown on the left is our proof of concept design, where we just had our sensors mounted to our testing fixture. We had all of our components exposed, and we just taped 2 motors to the helmet just to test to see if the device would function as expected. Next in the middle, we have a picture of our first prototype, and this design was basically a curved bucket that we mounted to the helmet that housed all of the components and all of the wiring and had feed-through reports for the sensors. The biggest lesson we learned from this design was that having all of that stuff on the back of your head was a little bit too heavy and felt uncomfortable when you would look around and move around. So this informed our final design that we've been going through, where we took out the battery and the microcontroller and put them in a component housing box in the backpack shown here. Finally, we have our circuit design. Mark went through our list of components that we used for this device earlier. We powered the device with a 6-volt battery. We stepped down that voltage to 5 volts, and then powered the rest of the device using that.
As we know, that ethics lie behind any engineering project, and the NSPE Code of Ethics states that engineership will paramount the health, safety, and welfare of the public. As we heard that many times today, we believe that's exactly what we're doing, because we're creating devices that better help hearing impaired riders, and we're decreasing the amount of collision prone slope. Also, the same code states that engineers shall acknowledge their errors and not distort the facts. And later in this presentation, we'll clearly display all of our data that we collected while doing our studies. Lastly, the ASME Code of Ethics states that engineers should strive to increase the competence and prestige of the engineering field. And that's exactly what we're all doing here today by having young people create devices that can better tomorrow's society.
So how do you test a device like this? If you look on the right side of the screen, you'll see an image of our testing area out in the parking lot. In this scenario, I was the user wearing Hindsight, and Mark was the other skier or snowboarder behind me. We started off by doing our static testing. Static meaning that the user was stationary during the entirety of the test. We then completed our LRC zone testing, our distance testing, and then a combination of the two. In this scenario, LRC stands for left, right, center, which refers to our 3 sensing and vibration zones. We then moved to our dynamic testing, dynamic meaning that the user was in motion during the entirety of the test, and that was done through our shred testing. It's important to note that during our period of testing, the average temperature outside was about 35 degrees. This is relevant due to the fact that this is a temperature that you would easily see on the slopes on any given day. So as for our LRC zone test results, basically how this functioned in this scenario, Corey was the user wearing Hindsight, and Mark was the other skier or snowboarder behind him. Mark was sent to a predetermined spot. So in the first one, it was a distance of 5 meters behind Corey in the right zone. So once Mark was there, Corey turned on the device and used the vibrations that he felt in his helmet to correctly determine where Mark was 90% of the time. We all went through this exact same test, and as a group, we averaged 75%. So that, comparing that to the control of 33%, that's 2 times better, which means we were 2 times more likely to be able to identify where someone was behind us due to the vibrations given by Hindsight. Finally, our distance test results. So on the left side of the screen here, you'll see our testing area. I, in this situation, was the user, and I'm denoted by this black circle. Mark, again, was the other snowboarder behind me. He's denoted by this blue smiley face. So how this test worked was, Mark was placed at a position 1 to 8 meters behind me, and I was I was supposed to basically say, you're at this distance for me based on the vibrations I was feeling. So in this exact trial, Mark was at 6 meters, but I guessed 5. So we then ran this 9 more times, and the results are shown on the right side of the screen here. I was able to get it correct 7 out of 10 times, but even when I was off, I was only off by 1 meter, as you can see here. The blue is denoted by the actual distance, and the orange is what I guessed, and that is shown exactly here. So as a group, the trend for the average distance differential carried out to be still about 1 meter. Even though the distance differential was quite low, our group average score was 43%, just above the control percentage.
So here for the results of our shred testing, we have a video. And in this video, you're going to see 2 panels playing simultaneously in sync. On the right, you're going to see me longboarding, and I'm wearing Hindsight. And Mark is going to come in from the right, longboarding. I guess the video doesn't play. So in this video, what's happening is that I'm longboarding, I'm wearing Hindsight, and then Mark is going to come behind me and enter my blind spot and go back and forth. In the left is supposed to be applied with motor speed versus time, and it's going to be color-coded spikes that show the sensors detecting me and the motor speed dialing up for the sensors detecting me. I was able to feel Mark's vibrations as he was coming behind me, and I was able to raise my hand and say he's on the right side of me or he's on the left side of me. But most importantly, what we learned is that you're able to tell the path of someone moving through your blind spot as they're passing behind you, because you can feel the vibrations going around the top of the helmet, either left to right or right to left. So in conclusion, Hindsight is an attachable blind spot monitoring system that aims to increase the awareness of skiers and snowboarders with impaired hearing. Through our testing, we found that Hindsight was effective at doing just that and increased the spatial awareness of the user. When we were doing our testing, we learned that there's a bit of a learning curve with the device, and that the more you use it, the more you're used to vibrations in the helmet, the more accurately you can identify someone in your blind spot. While we did see some positive results from our testing, we do recognize that there's definitely room for improvement in our device. So we would suggest looking into different sensing methods, or looking into more intense vibrations to increase the reliability of the device and the accuracy of identifying someone in your blind spot. And then finally, another pathway for improvement is designing Hindsight such that it's an integrated design into a helmet that evenly distributes the weight of components across the helmet while still maintaining the safety requirements needed for a helmet. So here's our references. And for our acknowledgements, we'd like to thank Dr. Wu for advising us during the semester and pushing us to keep working. We'd like to thank Dr. Zhu for guidance with circuit design and component selection. We'd like to thank Dr. B for keeping us on track and letting us use his lab. We'd like to thank Public Safety for letting us in that lab countless times. We'd also like to thank Active Angle for being supportive of our project and going through this process.